The next couple of fields I want to talk about are the next header and hop limit fields. And we'll start with the next header field, which is located in the 6-byte offset from 0 in the IPv6 header. You'll see that there in the second row right after payload length. Now, the next header field essentially replaces the protocol field in IPv4. And if you remember, the protocol field tells us what the transport layer protocol is or what the embedded protocol is. Basically, for the receiving system, it tells it what protocol is next, so it knows how to dissect it. The next header field does essentially the same thing, but instead of being called the protocol field, it's called the next header field because it is a little bit more descriptive, first of all, but also in the fact that the next header may not necessarily be another protocol. I mentioned earlier that IPv6 has a concept of extension headers, which allows it to implement additional features such as fragmentation. So the IPv6 header is always a static 40 bytes, but if it wants to provide any additional functionality, it does so via extension headers that are added on to the end of the IPv6 header or added after it. The next header field, when those are present, will identify that as the next header. So the next header may not actually be the transport layer protocol as it would be with IPv4. It's just another header, and the receiving system needs to know how to interpret that. So we'll talk about extension headers here in just a moment, but know that the next header field is really essentially the same as the protocol field, but can do a couple extra things in regards to extension headers. The next field is the hop limit field, which comes right after the next header field. It's right before source IP address, and it's at byte offset 7 offset from 0 in the IPv6 header. Hop limit is essentially the same as the TTL field in IPv4, just with a different name. It's functionally the equivalent for the most part. There are a few weird discrepancies with how TTL is described in IPv4. For instance, TTL stands for time to live, and in the original spec, TTL can actually be a time-based mechanism and not based upon router hops. Since in IPv6 it is more based on router hops, they've actually changed this just from TTL to hop limit because it's a more descriptive name and more accurately describes the process that's happening here. But for our purposes, you can think of hop limit pretty much the same as TTL was in IPv4, and that again is in the 7th byte offset from 0 in the IPv6 header. One of the big goals with IPv6 was to provide a more efficient mechanism for being able to extend the header, first of all, in a more predictable way, but also in a more flexible way. And IPv6 extension headers really make that possible. They make it quite a bit easier to do that sort of thing than with IPv4, where you have the variable header length and options can come in a variety of different ways. IPv6 uses extension headers, which is essentially just an additional header that's added on after the IPv6 header to provide additional functionality. So the IPv6 header is always 40 bytes, and then you have the ability to use the next header field to identify additional functionality through another header. So for instance, fragmentation is a good example. Fragmentation is handled now through an extension header instead of being part of the primary IPv6 header itself. And with good reason, right? We don't use fragmentation near as much these days. We still have some use cases for it, but if we're not using it in most of the packets, why include those fields? That's just additional data that makes the header bigger than it needs to be, more complicated. More processing has to occur that's essentially wasted if it's not being used. So that's the reason why it's an extension header. But I do want to talk a little bit about how that works and how you'll visualize extension headers when dealing with IPv6 traffic. And I want you to imagine that we have an IPv6 header here, and then we have this next header field, which specifies what the next header is. Remember, this is working functionally kind of equivalent to the protocol field in IPv4, so where it tells the recipient system of the data what protocol it has to dissect next. Now, in a typical scenario when there are no extension headers, the next header field will identify what the transport layer protocol is. So in this case, it might identify that it's TCP using the value 6. So that tells the recipient system to dissect that the following data as TCP, and then that data would be followed by a TCP segment. That would be the breakdown of that part of the packet there. So this would all be one thing. But let's say we want to use an extension header. In this case, the next header will actually be identifying what the extension header is. So let's say we want to use an IPv6 routing extension header. We would identify that, and then the routing header would come in after that. And note that the routing header would also have its own next header field where it would identify what's next after that. At this point, IPv6 header, routing header, we're still at the network layer. We have to get up to the transport layer at some point, and the following next header field in the routing header is going to do that, and then we would see the TCP segment. Now, the cool thing about this is you can chain as many of these extension headers onto the end of the IPv6 header as you need to. So same example, we have an IPv6 header, packet header, and we identify the next header as a routing extension header. So we include that. But in this case, instead of identifying the transport layer protocol TCP next, it identifies a second extension header. This time it identifies 44, which is fragmentation. And so we have the fragmentation header here as well, still all at the network layer. The fragmentation header then identifies 6 or TCP as the next protocol or the next header. So we have the TCP segment there. So you can string as many of these together as you see here. And I find this is the best way to visualize what's going on and how the next header field works. Very simple. It just tells you what's next, and what's next can go on for quite a few steps before you get to before you leave this layer and go to the transport layer, where the rules change, and then we're bound by whatever the rules of the transport protocol, such as TCP and UDP, what those rules are. I just switched over to an IPv6 packet capture because I want to show you an example of extension headers, not just in theory, but in practice as well. So we're actually looking at a file called IPv6_fragments.pcapng, which is basically an example of fragmentation similar to what we looked at earlier, where I was pinging from one host to another, but the packets had to be fragmented because of a lower MTU setting than what was trying to be sent. So that's exactly what we have here. But I want to show you the extension header and the kind of the structure of that. So in this case, I'm just highlighted packet 1 here. I'm going to expand the IPv6 header. So we see a lot of the fields we've talked about. So if I highlight that, you see it's going to highlight that chunk of data down below. We see IP version 6. We see payload length and so on. Hop limit as well, source and destination, IPv6 address. Now, of interest here, notice the next header field says that the fragment header for IPv6, or value 44 here, is what's next. So we don't have a transport layer protocol, we don't have ICMP, we actually have a fragment header for IPv6 present. I go down here and we see that listed. So we see fragment header for IPv6, and if I expand that, that data is going to be available here too. And it has a lot of the same things we expect to see related to fragments in terms of how IPv4 also handled fragmentation. We see a fragment offset, we see reserved bits, we see more fragments, we see identification. So we see a lot of the things we would expect to see there. Fragmentation kind of works for the most part in a very similar way. We're just placing it in a different area with the fragmentation header. Of course, if I click on that, you'll see that that's a pretty short header and it's following the rest of the IP data. So if I click on destination, that's occurring right before, and go to the fragment header, and that's occurring right after. And you can see that change taking place when I click in the packet bytes window below. This starts with this 3A00 here. So pretty straightforward. However, notice that the fragment header has also its own next header field. So any extension header is going to have this, and they're going to tell us what's next. That's the job of the IP header in this case, is to tell us what's next, whether that's another extension header or whether that's a transport layer protocol. Or in this case, it's actually ICMP. It's something we're going to talk about here in a minute. It's ICMPv6, and that's the next header. So if I highlight this fragmentation header, you'll see here it ends at 0817. And then if I go down here and click into the data portion, just following that, we see we get 8000. Now you might be asking yourself, well, why don't we have an ICMP header here? And that's because we're looking at the first fragment in this group of fragments. If I go down to packet 2, we now have the ICMPv6 header, because remember, when you have fragmented packets, it's only on the final fragment of that fragmentation train that the assembled protocol is available for you to look at. That's just how Wireshark chooses to display this information. So we have then our IPv6 data, which is going to have the things we expect from ICMP data. So pretty straightforward how extension headers work. Just keep in mind that the most important field when thinking about fragmentation, or excuse me, about extension headers, is the next header field, because it tells us what to expect next, and it also tells the recipient system what to expect next when analyzing packets and dissecting them.